Now that we've found the percent error in the molarity of the original ammonia stock solution, we can complete our calculation, and from here I think you'll find that the calculation becomes pretty straightforward. Having found the error in the molar concentration of the ammonia, we can now take that into our actual calculation where we used M1V1 equals M2V2 to calculate the concentration of the more dilute ammonia solution. Because we're using M1V1 equals M2V2 to calculate the concentration of the diluted solution, the error is still propagating according to multiplication and division rules. So the error is propagating as the relative error in each quantity: the original stock solution's molarity, the volume that we took out, V1, and the volume we diluted it to, V2. Here is the 1.8166% error that we just found in the molar concentration of the ammonia. And we take the relative errors that we previously calculated for V1 and V2, 0.4728% and 0.04%. We square each of those relative errors. We add them together and we take the square root to determine the overall percent error in the concentration of the more dilute solution, M2. So the percent error in M2 is going to be 1.877%, taking the square root of that whole thing. Now notice that the error in the concentration of M2 is mostly due to the error in the concentration of the original ammonia stock solution, which we can say because this is a significantly higher percent error than any of the other two. The percent error in V1 contributes a meaningful amount, quite a bit more than the second volume error, but by far the vast majority of the error is due to the random error in the original ammonia stock concentration, because the 1.8166% error in M1 is very similar to the 1.877% error in the second concentration. To find the absolute error, we have to unpack this percent concentration, divide it by 100% to make it a decimal, and we will take 0.001877 times the concentration of the dilute ammonia stock solution that we determined, 0.250 molar, to get our final absolute error in the molarity of the dilute solution. The absolute error in M2 is plus or minus 0.005 molar. So this is a tricky problem, but the thing I want you to take away from this example problem is primarily that even when you have a seemingly difficult problem where you have to propagate the error through quite a number of calculations, take a look at the calculation that you use to calculate the results you're interested in and just identify all the sources of error in it. If you used multiplication and division to come up with your final result, the error will propagate by multiplication and division rules. If you have one source of error in that multiplication and division, which came from multiple sources itself, take that back a step farther, look at how you came up with that number, and then use the appropriate rules to determine the propagated error in that number. Then you can take that error and put it into the general formula that you use to propagate error in your final result. So you always treat error stepwise, calculating the error associated with each measurement one at a time using the propagation of error rules. This can seem tedious and like it's taking a long time, can be a bit painful, like pulling teeth sometimes. But if you keep your head about you and you go through the thought process systematically, calculating the relative and absolute errors one step at a time, you will get to the final result, and this will start to resolve itself and it will get easier. I expect that you guys have some questions on this, so remember, I'll be online today during our standard class time and during afternoon office hours, so please feel free to throw any questions you want at me about propagation of error during that time. I hope I'll see you then.